Good day everyone and welcome to this lesson. In this video, we will be talking about ecosystems, their function, their structure, and what are our impacts to the ecosystem. Before we dive into the technical details about ecosystems, let's first refresh your memory about the spheres of the Earth. These spheres are the major subdivisions of Earth that are distinguished by their boundaries. So we have the atmosphere dealing with the air, we have the hydrosphere dealing with the bodies of water, we have the lithosphere dealing with the bodies of land, and at the middle, at the intersection of those three spheres, we have the biosphere, which encompasses all living species. So you see that the spheres of the Earth here are represented as a Venn diagram, wherein each intersection represents an ecosystem. So let's define what an ecosystem is. It's a combination of biotic and abiotic factors that interact together. When we say biotic factors, these are the living species, these are the things found in the biosphere. And when we say abiotic factors, these are the non-living things. These are the non-living things, and these are represented by the lithosphere, hydrosphere, and the atmosphere. These are intersections between the biosphere and any of the three other spheres. So if we go back to the Venn diagram, the biosphere has intersections with the atmosphere, hydrosphere, and lithosphere. So let's say, for example, the intersection between the biosphere and the hydrosphere would be the lakes and the oceans, wherein part of the hydrosphere is the water and part of the biosphere is all of the life living on those waters. Another example is the intersection of the biosphere and the lithosphere. Those would be your grasslands, forests, wetlands, etc. However, ecosystems are not just limited to the intersections of the four great spheres of the Earth. We can also call man-made creations as ecosystems, as shown here. Lakes and grasslands are examples of the intersections of the hydrosphere and the lithosphere with the biosphere respectively, while the biological waste treatment plant is an example of a man-made ecosystem. Granted, there are no animals or plants living on this type of ecosystem, but if we consider bacteria and other microorganisms, then the biological waste treatment plant is a very big and rich ecosystem. So what's common with these three examples of ecosystems is that they all share the same energy source, and that is the sun. And that's because the sun is the source of all energy on Earth. So everything is a derivative of the energy coming from the sun. But these ecosystems do differ in their primary consumers and producers. For our study of ecosystems, you still have to recall your past learnings about environments and ecosystems, but we will be adding some technical details to your understanding of ecosystems. First, the concept of carrying capacity. So we have already tackled carrying capacity in our previous lesson. No? The carrying capacity is the maximum amount of population that a certain environment can sustain with its renewable resources. In here, we interpret the carrying capacity as the same. In a balanced ecosystem, natural limits are imposed on the population of organisms. The natural limits that are pertained in this example are things that limit the population of a species. That includes diseases, predators, limited space, and overall limited resources. In theory, there is a maximum limit for the existence of every species in an ecosystem. With many species occupying a single ecosystem, we have to talk about population dynamics. Population dynamics pertains to how a population of a certain species grows and shrinks depending on the pressures exerted into it, both natural and artificial. The population growth in an ecosystem is not without bounds, as stated by our definition of the carrying capacity. Thus, it is limited by the amount of resources. This graph shows us the growth of biomass as well as the specific growth rate of a certain organism with respect to time. You see that the biomass curve follows the logistic model. This is what we have discussed in our previous lesson, but the specific growth rate follows the opposite curve. So as your biomass increases, meaning as the population increases, the specific growth rate of the population starts to decrease. We are also seeing this in the population dynamics of the people on Earth. I have mentioned earlier that since 1965, our growth rate has started to continuously decrease. That's because we are nearing the capacity of our population. That's the same with other species. There are limits imposed on their population based on the amount of resources. That's why their specific growth rate starts to decrease if their population is already big. Okay, so this is an ideal scenario wherein you are in a closed system. But what really happens in reality is pictured in this next graph. So this graph shows you the resources denoted by the letter S and the population denoted by letter X. At the beginning of the graph, we have plenty of natural resources, but our population is small. As our population grows larger and larger, the amount of resources starts to decrease, which is logical because we are using our resources and we are exceeding our carrying capacity. That's why our renewable resources are starting to dwindle. As we are reaching the peak of our population, our resources continue to decline up to such a point that our resources are completely depleted, and that leads to the downfall of the population. This is what we call a die-off. If you compare this to the graph of our population, we are still at the exponential growth phase. That means that we have not yet depleted all of our resources. But the moment that we have depleted all of our resources, expect that our population would experience a die-off. So this is what happens to species in ecosystems. We should also expect that this is what's going to happen to our species as our resources continue to dwindle. That's why sustainable development is very important. And that is to prevent the complete exhaustion of our resources, thus preventing the collapse of our population. Okay, going back to ecosystems, the logistic curve that I have shown you earlier, which is a model of the population growth of a species, is anchored on a big assumption that we have no competition or that there's no competition between other species. However, that is not true for all species. In real ecosystems, there is competition between species, and competition imposes a limit. Organisms sharing the same resource will compete if introduced to a closed ecosystem, and it can sometimes lead to one species dominating. This is an example of competition in ecosystems. We have two species of paramecium. When they are grown separately, you see that their growth both follow the logistic model, and they both grow up to the carrying capacity of the system. However, if you mix these two species together, only one species dominates, the other species starts to dwindle. That's because they are competing for the same resources. Okay? This is what happens to real ecosystems. If two species are competing for the same resource, expect that one species would prevail, the other species would be subdued. But that does not mean that the subdued species would be totally erased. That depends on the ability of the subdued species to adapt to new environments and to new resources. Now let's talk about food webs. Food webs and food chains are something that you have already talked about when you were in elementary school. So what we were taught when we were younger is that the producers are plants, they produce food, the primary consumers eat the plants, and then the secondary consumers eat the primary consumers, and so on and so forth. But what we will be discussing about food webs here is the technicality of the energy flow in this ecosystem. So energy is transferred through the ecosystem by consumption. The energy produced by the producers are transferred to the primary consumers when they eat the producers. The energy stored in the primary consumers will be transferred to the secondary consumers when they are eaten, and so on and so forth. So that represents energy being transferred through species in the ecosystem. Energy moves upward through trophic levels. So these are trophic levels: producers, primary consumers, secondary consumers, and tertiary consumers. And energy is expected to move upwards from the producers to the tertiary consumers. Consumers higher in the trophic scale needs more food to sustain them. So that means that the tertiary consumers would need to consume more secondary consumers, and the secondary consumers need to consume more primary consumers, and the primary consumers need to consume more producers in order to keep the balance of the energy flow in the ecosystem. This is a closer look into the energy flows in ecosystems. Represented here is a single food chain wherein phytoplankton are your primary producers, zooplankton are your primary consumers, and then you have fishes as your secondary and tertiary consumers. The energy flow in the ecosystem is represented by several processes. Two of those important processes are photosynthesis and respiration. Photosynthesis is the process that the primary producers use to convert energy in the form of sunlight to food in the form of starches and protein. And respiration is the process wherein the consumers digest their food in order to obtain the stored energy. Just a quick review, no? Photosynthesis is the process of food production by plants. If we represent photosynthesis in terms of a chemical reaction, this is it. That would be carbon dioxide plus water plus energy yields carbohydrates plus oxygen. These carbohydrates are the stored energy in the plants, and if they are eaten, this carbohydrate will be the energy source of the consumers. Now, this energy is largely coming from sunlight. Energy from the sunlight is needed to split these molecules and to form carbohydrates. The opposite of photosynthesis is respiration. In respiration, the stored chemical energy in the form of carbohydrates are oxidized to form back carbon dioxide, water, and usable energy. Now, respiration is done by both producers and consumers. So plants also respire because plants also need a mechanism for them to use their own stored energy. Now, let's take a closer look in the energy transfer through trophic systems. If we are performing mass balances, which means that the mass going in should be equal to the mass going out plus the mass accumulated, that means that if you are a tertiary consumer, the mass that you are building into your body should be equal to the mass of the food that you are eating. But we know that that's not the case because we also excrete waste and there's also energy losses as you jump from one trophic level to the other. So let's talk about energy losses. The energy losses through the ecosystem is represented by a lot of factors, and that if you subtract all of the energy losses from the energy intake, that would give you the net energy available to the consumer. Okay? So not all energy ingested by consumers are converted to usable energy because of energy losses. So here are some phenomena that factors into energy losses. You have egestion. Egestion is the practice of excreting undigested materials. Excretion is the process of releasing digested materials. You also have respiration, which uses up your stored energy. And you also have death of the organisms. So if you subtract all of these factors to the total amount of energy that was ingested, then your net is your energy available to consumers. So as humans, we are at the top of the food chain, so we can be considered as tertiary consumers. That means that we need more energy coming from the lower trophic levels to fulfill our needs. And with our ever-increasing population, that means that the lower trophic levels should be working overtime to produce more biomass that can be supplied to our population. We can represent energy losses in terms of this pyramid here, wherein primary producers are at the very bottom and us tertiary consumers are at the very top. You see here that a certain portion of the available energy is allotted for both decomposition and respiration. And as you go up through trophic levels, that amount of energy starts to decrease and decrease. This also explains the distribution of species. So there should be more primary producers than primary consumers. There should be more primary consumers than secondary consumers, and tertiary consumers should be the least represented species in an ecosystem because they need more food to sustain themselves. That's why if you take a look at a natural, untouched ecosystem, you see that the species with the least population is the apex predator, and the species with the most population are the primary producers. And that is to keep a very fragile balance in that ecosystem. Okay? So with humans entering that landscape, what happens is, since we are tertiary consumers, we are disrupting the rule that the apex predators should have the least population in the ecosystem. And that leads to overshoot in our carrying capacity. That also leads to the overexploitation of our food sources. Next, let's briefly discuss about ecosystem health. Ecosystem health is simply the measure of the relative condition of the ecosystem. So is it still healthy or is it not? You can liken ecosystem health with human health. So if we are not healthy, you can tell that something's wrong, something is out of balance. That's the same with ecosystems. Questions that might be asked is the ecosystem still balanced? This pertains to the balance between biotic and abiotic factors. And can it adapt to counter stresses? If an ecosystem can still adapt, even if there are a lot of stresses, then that is a very healthy ecosystem. Is the ecosystem under stress factors? So these are some stress factors, some are natural and some are man-made. Climate related, that's flooding or drought, invasive species, loss of biodiversity, fires and deforestation, extinction, and other man-made stress factors. So these stress factors are what causes for the health of the ecosystem to deteriorate. However, this concept of ecosystem health is sometimes flawed because it's very subjective. The assessment of the health of an ecosystem would be largely dependent on the type of activity that is intended for it. So, in some ways, the wrong and exaggerated interpretation of ecosystem health goes against the concept of sustainable development. Okay, so you have to be careful. Ecosystem health can be subjective. Now, before we close this lesson about ecosystem, let's introduce the Anthroposphere. Earlier in this lesson, I have mentioned that we have the four great spheres of Earth, the hydrosphere, atmosphere, lithosphere, and biosphere. Technically, the biosphere should include all living things, including humans, but because the impact of humans has been very, very big compared to other living organisms, it has been necessary to separate humans from the biosphere, and we call that the Anthroposphere. And in this figure, the Anthroposphere encompasses all of the other great spheres of the Earth because we derive all of our resources from the hydrosphere, lithosphere, atmosphere, and the biosphere. So, in a way, we are the custodian of all of the other spheres because we extract everything that we need to live from the other spheres. However, since we are encompassing all of the other spheres of the Earth, we have several negative impacts that need to be addressed urgently. And those are climate change, land degradation, water and air pollution, and disruption of ecosystems. This is because we need to extract more resources to feed our ever-growing population, and our desire to extract more and more resources is encroaching into ecosystems. However, not all of our impacts are negative. We can also turn those into positive impacts, and those positive impacts are our solutions. Those are climate action, restorative land use, sustainable utilization of resources, and the most important is the concept of cohabitation, wherein we respect the other organisms that are also inhabiting this earth. And those are all parts of our goal of sustainable development. For further reading, I would encourage you to read about keystone species, and I want you to know their functions in the ecosystem. A very good example of a keystone species are sharks. And since shark populations have been dwindling worldwide, the balance of ocean ecosystems have been disrupted. I want you to learn about how the removal of a keystone species leads to a collapse of the food web. Okay? And that ends our lesson. I hope you have learned something. If you have questions, don't hesitate to message me. And as always, keep safe.